Hello, welcome to this lecture. In this lecture, we are going to deal with shot noise. It's a very significant and fundamental source of noise, which arises out of randomness of discrete events. So, if you think about shot noise, in the context of electron current, it arises because electrons are discrete. The charge on the electron is discrete. If you think about arising out of detecting photons, then the individual photons being discrete leads to a short noise. So we will see that these are events which are occurring randomly in time, which are independent of each other, and there is a uniform probability that any of those events can happen at any time within a given time interval. So these are the kind of events that we are going to study, and we see that this is at the heart of how current, for example, propagates uh, within within electronic system. So consider the following situation. We're always looking at events which involve a flow of discrete particles, as I mentioned. So here, the events of interest is this electron flow within a certain volume. So imagine that A and B are basically two um, metallic plates, and one is talking about a region between these two plates A and B. And what happens is that this region, for simplicity, is simply vacuum. And one has maintained B to be at a slightly higher potential in comparison to A, right? One has attached a battery here, which you can see. So this particular battery is helping B be maintained at a higher potential than A, and electrons are periodically released from the plate A, right? So on an average, there is a certain emission rate, right? Number of electrons per unit time, and that is simply given by the average current divided by the electron charge itself, right? So that is the typical situation one is talking about. The charge carried by the electron is minus E. One talks about of an instantaneous velocity of the electron. Let us call that V of t. And you see that the event that we are interested in is this single event wherein one electron goes across from terminal A to terminal B. So that is the event that we are trying to capture. And the current due to this single electron, right? This current pulse is basically the charge times essentially V of t by d, d being the distance between the two plates. This simply gives me a time scale on an average which the electron takes to go from A to B, right? So that essentially is my current pulse arising out of a single electron. So the way to obtain the current due to a single electron is to undertake this following exercise. So what one does is basically uses the Gauss's law in the integral form. What you have on the right hand side of the Gauss's law is a source term. So here the source is basically this plate. We are looking at a uniform plate of cross-sectional area A that is parallel essentially to the plates A and B, and a charge minus E is uniformly distributed on that plate. So we are looking at a sheet of charge essentially moving between the plates A and B. Now this sheet of charge instantaneous velocity is V of t, right? And because of the sheet of charge, one can actually calculate, for that matter, the what is the induced charge in A and the plate B, right? So this induced charge is what I have written down here. You can do this calculation yourself. And similarly, there is an induced charge on the right hand side, which is Ex by d. Now, if you look at this, d minus x is the distance between this infinite, rather this finite sheet of charge and the plate B. whereas x is the distance from plate A to this sheet of charge, uh, which contains a single electron smeared across this whole plate. Uh, Right. So the current in the external circuit is basically current due to this single electron going across the plate A and B, and that is simply the change in the charge in the induced charge in the right plate. Right. So one can obtain that. So take this and take a time derivative, and what we get is E times v of t, which is the instantaneous velocity divided by d. Right. So that allows you to now look at that single event, as I said, which is central to our discussion. Right. So the single event, if you recall, when we looked at the spectral density function of such events, we had an event in time. That is precisely what we have here. um, so you have an event that is occurring between time 0 to ta, right? Ta being the arrival time of the electron that has been emitted at t equal to 0, right? So 0 to ta is an interval the electron takes to go from plate A to plate B. And what we are doing is looking at the Fourier transform of such an event. So E by d times v of t was indeed the current. 1 over 2 pi is coming from the Fourier transform, and exponential I omega t is the Fourier kernel. Right. So then if you now make a simplification, which is of the kind that if you look at these arrival times, the statement one is making that the arrival time is extremely short in comparison to the frequencies that we are interested in. So the Fourier transform, of course, gives you a spectrum in the kind of energy in the frequency domain. But the frequencies that one is interested in is typically limited to, let's say, megahertz to at most gigahertz. But you see, if I just consider a typical situation where I have a 1 micron distance where the electron needs to go from one end to another, and I put in a voltage of 1 volt, you see that then typically the time scales required for such a uh, ballistic propagation of the electron from one end to other is basically 10 power minus 12 of a second. That's a picosecond. Uh, Whereas the kind of frequencies of interest for us is basically, as I said, from megahertz uh, to about gigahertz. Right. So the f of omega, given such an approximation that omega times t is much smaller than 1, I can replace my exponential minus omega t by just unity. So you see that what I get is basically dx over dt, and I can clearly see that my the frequency in the frequency space, the Fourier transform of the single event simply comes out to be e by 2 pi. Of course, this approximation that we have made, that your omega t is much smaller than 1, is not necessary. I would request you to indulge in the exercise where exponential minus omega t is taken as it is, and one can essentially get similar result, which is a slight generalization when you are talking about higher frequencies. So anyway, other point to recall here is this blue box, which is simply telling you that the spectral energy, spectral density function, right? It's simply given by 8 pi square, n being uh, the rate at which the events are happening, and f of omega is basically telling me the Fourier transform of that single event, right? This was precisely what the spectral density function that we had derived earlier. So this f here will be played by the f of omega that we have just obtained, and let us see what we get ahead. Right. So if I plug in these forms here, remember n bar was related to the average current. Remember that was simply average current by the charge itself, right? So that gives me n bar by E. There is E by 2 pi whole square, which is arising from the f of omega, right? Whole square. And then, so effectively what we get is a number which is quite interesting. It is 2 times the charge of a single electron, which is responsible for that single event, the average current, which is like a DC current that is flowing through the system, and d nu is giving me the range. And clearly see the first observation being that this noise is sort of white noise, right? It is a noise that is uniform across all frequencies. There is no frequency dependence in this prefactor, only the bandwidth of the appropriate frequency range comes in, and this is more or less frequency independent. So this is the spectral density function associated with short noise. Now let's look at it more closely. You see that clearly the short noise is proportional, if you like, to the charge itself. The fact that my charge is finite, I can never get rid of the short noise, right? Only in the limit that imagine that my charge was tending to zero, right? Only in that case you would see that indeed the short noise will go away. So it's a very fundamental noise, and you see clearly that it is proportional to the uh, DC current, the I bar, right, which is my average current flowing through this circuit. Interestingly, this is a noise that is occupied at all the frequencies S of nu, d nu, and one can look at any part of the spectrum. So one is not restricting ourselves only to the DC part of the spectrum and call it a DC noise. It's basically AC noise, right? Because it's there in the uh, every part of the spectrum. So it's a time dependent noise. Interestingly, this AC noise is arising out of a DC current, right? The I bar being a simply current proportional arising out of simply the rate at which these events are happening. So it is proportional to the DC part of the current, and yet it occupies the uh, noise occupies the frequencies which are higher than DC, right? And we will see quickly that the ratio of fluctuations to average current, right? So this is essentially noise. So one is asking now what is the ratio of the fluctuations which are arising out of short noise, for example, to the average current that is flowing. And we will see that as you increase the number of events, right, this ratio will actually come down. That would mean that the notions of short noise are less uh, sort of are affecting are not so detrimental, okay, when you have large flow of current, right? So we will come to that. So now one can associate, for example, an equivalent noisy current source in a circuit, right? One can have this as my source of noise, and this source of noise will simply will involve a current source whose power levels are of this kind, which is simply 2 times E times the average current times d nu, right? So this is essentially the main result arising out of short noise. So let me just now further talk about the the distributions that one can talk about. So for example, the events which are happening, which we considered here, are basically random events which are occurring in time. So if I look at a time duration capital T, I am asking what is the number of events that are occurring of this kind, which is that electron flowing from point A to point B. Clearly, these events are happening randomly, and imagine that n bar is my average number of events over this interval. Then such random events are governed by something called the Poisson distribution. I'm sure you're familiar of this, uh, but this form is very important. This is a distribution. So you see clearly, if I integrate over all possibilities of number of events that can happen in capital time T, let's integrate from 0 to infinity, Pn dn will give me 1. So Pn indeed forms a probability distribution. On the other hand, if you look at so this exponential minus n bar is basically arising out of some sort of normalization, right? So you see that n bar to the power of n divided by n factorial will essentially give you kind of a exponential the term when you sum over all, and this exponential minus n bar is basically make sure that you indeed land up with p of n being a distribution, right? Now n being the number of events in the observation time, n bar here is the average number of events in that time. So you see I can basically look at what is the average number of events in the that is, I'm looking at n times p and dn. If I do that, so this is precisely the exercise I am undertaking here. I've written down the Poisson distribution and I'm looking at n times that. So you will see that once I multiply by n, I can cancel out this n minus 1 factorial as just a number. Remember that I need to integrate this n from 0 to infinity, right? So I'm calling this n minus 1 as another dummy variable m. So you see that this particular factor will actually give me the Poisson distribution again. So you see that once I sum over it all, I will get back my n bar being the average number of events, right? Now similarly, to look at basically the variation of it, I can look at n square as well, the average of n square, and you see that is going to be this is a little trick that I use, algebraic trick. I can write down n square as n into n minus 1, and that will give me n square minus n. Then I add a plus n to it, and you see that because everything is linear, I can look at the average of this term, this product, and the average of this, and you see that one can quickly use the above tricks of looking at n factorial as n into n minus 1 into n minus 2, and basically cancel out these terms and so on, and you can come up with this result. Okay, I urge you to do the algebra yourself, and then one can look at what is the fluctuations in this, which is basically looking at n minus n bar and whole square, which simply happens to be, you can open up this bracket and then average it, and you see this averaging will give me basically the n square average minus the average square, right? And this quantity you will see actually is proportional to the average number of events itself. So if I now look at delta n, which is the square root of this, this is going to be square root of the average number of events. So if I'm looking at the ratio of these fluctuations to the average current, right, ratio of this number, you see that clearly no, these the fluctuations essentially go like 1 over square root n bar. That would mean that this ratio actually decreases as you increase the number of events. Let me just illustrate this precisely in terms of a very simple example. uh, Imagine you are playing this game of tossing coins. So you have a coin which can give you either heads or tails, and you see you are going to toss this coin multiple times. That's a game. Now imagine that the number of times you toss the coin is very small. So you see that if you count the number of heads and tails for multiple of such events which involve only tossing the coin, let's say only a few times, like 10 times, you will see that there will be large variations between number of heads and tails that you come up with. Whereas if you had done the same coin tossing experiment, let's say 500 times, you would see that eventually you will, in terms of statistics, you will find that there is an equal probability of getting heads or tails. But when you look at this very short times with few singular events happening, you see that the noise is really large. So this is precisely what is captured by the short noise. Look at that noise where you're looking at a few events, and as you increase the number of events, you essentially decrease this feature or the noisy feature arising out of this individual events, right? So that is the mental idea they can keep. But here, of course, we are talking about now this discrete flow of random events, which is in this case the flow of electrons from one end of your system to other end. Now you see, this is essentially short noise, but you see that this can have details. For example, there might be materials where between A and B is not evacuated. It is actually a finite piece of semiconductor where other kinds of events, kind of contribute to the randomness that is arising in the flow of electrons through that. So we will put in all these kind of features, uh, you know, and basically analyze what short noise is. But this is simply a general introduction to this idea of short noise, which simply depends on the discreteness uh, of that event. There is a particle-like behavior that is responsible for the event, and uh, it is only when the finiteness of the particle can be gotten rid of that you can get rid of the short noise. Essentially, you can never get rid of the short noise until and unless you get rid of the particle that is responsible for the noise itself. So hence this is a very fundamental source of noise, and indeed it becomes worrisome only when you are looking at extremely low levels of the signal itself, right? When you are looking at extremely low signals, which are sort of comparable to the most minimum noise that you can make your detector to have. Only in these cases you see that you cannot beat this limit arising out of the short noise, which is essentially a very quantum like, a particle nature like character. So in the next lecture, we are going to essentially study another very important contribution to noise, which is called the Johnson noise, arising precisely because of the finite uh, temperature of the detector arising out of essentially thermal fluctuations in such a system.